Okay, this is the final lecture video for the fall semester, which I know everybody's thrilled about. So before we get to the final reactions of alkynes, which will be our final topic for the semester on Friday, I want to show you that and just spend the time here talking about the course evaluation. So I'll probably reiterate this on Friday, but I've now placed a course evaluation box on Blackboard at the top of the page for your lecture section. And I do the course evaluations electronically, so we don't have to spend time in class for you filling them out. The course evaluation is your opportunity to assess sort of the effectiveness of the class. Not necessarily what you liked or disliked, but what was effective, what you thought was helpful in learning the material, if you have suggestions on things that might be done to help you learn the material a little bit better. Those are places for you, there's places for you to comment in the course evaluation. Now, I'm sort of obligated to assess you at the end of the semester by giving you a grade. And this is your opportunity to assess me and, well, really assess the course in a formal way, and that's what the course evaluations do. RateMyProfessor.com is cute. It's sometimes funny. It's most times brutally vicious, but it's not an official way for you to give feedback about the course. The course evaluation is where you can do that. Now, what will happen is this is a survey, and so it's actually not linked to anybody's name. All I will see at the end of the period of when it's due is simply a box that's a checkbox that said you turned one in, and I won't see that until after the grades are submitted. So if you click on the course evaluation, you're going to see, well, you can begin, and you're going to see basically the same type of survey that you may see in your other courses. Questions about what what year you are, grade point average, your expected grade, reason for taking the course, and then a bunch of questions that deal with the course material. And so these are what are called a Likert scale. It's basically strongly agree to strongly disagree. And then at the end of this, I've actually put some questions in because I'd like to get some more feedback about what you thought of flipping the lecture, and in particular how you're using the lecture videos and the quizzes and the online quizzes and the homework problems. And so there's a few questions here at the end that I'd like you to give me honest answers to about how you used the videos, how you used the homework problems and online quizzes during the course of the semester. And so there's a few of those questions. And then at the end, there's a place for you to type out some things. I'd like to know if you found any advantages or disadvantages or positive or negative aspects to flipping the class versus maybe the other traditional lecture science courses that you have been in or are in. And then, of course, you have the ability in the final box to give me a comment on anything you'd like. Realize that I will be looking at these comments in between probably Christmas and the beginning of courses next semester. And so if you have some ideas about, well, this would be more effective, or, could you do more of this? Could you do less of this? I'll take the less of this and probably with a little bit of advisement. But could you do this? I found this important, or I found this useful. Please put it in there, and I will certainly take it into consideration as I begin to sort of look at next semester. So if there's something you like that you want to see continue, or something you found useful that can continue, then please tell me. If there's something that wasn't so useful, you can tell me that as well. So the course survey will remain open until December. It'll remain open for you to fill out until December 14th. And then after grades have been submitted on December 17th, it'll be released back to me to then compile all of the statistics for your answers. And again, this is a survey, so the answers are not related to any particular person. They're just random. And that's the way Blackboard handles a survey. Okay, so that's what you will do. Maybe later I'll fill one out for myself. Actually, I can't do that, so that's a joke, just in case you're thinking I'm serious. So you can go ahead and fill out the course evaluation. It will remain open, like I said, until December 14th at midnight. So that'll give you plenty of time to sit down and go through it. And of course, you can do a little bit at a time and save things as you go. Now, I really don't need to provide incentive for you to fill out a course evaluation. You're kind of obligated, like I said, to assess me as I'm obligated to assess you. But at the end of the, let's see, at the end of the period, or at the end of the, when they're due, I'll see check boxes if you turned one in or didn't turn one in. And so you don't have to turn in one with answers. You can turn in a completely blank one that says not appropriate and, no comment. And either way, I will drop an extra quiz for those that turn it in by the 14th. So there, that's sort of the incentive I give to, sort of turn in one of these course evaluations. But really, I think you're obligated to give me some feedback, honest feedback that I can use, both positive and negative, so that it'll help me design the course for next semester, particularly if you're going to be in the course next semester. Okay, so that's about the course evaluation. Okay, so now let's talk about the last set of reactions for alkynes. And one of the things that is going to make this relatively straightforward, at least part of this, is the fact that if you know the reactions of alkenes, you know the reactions of alkynes. So we can add HX, which would be, again, our HCl, HBr, HI. We can add these to carbon-carbon triple bonds. They will add Markovnikov, and there's no stereoselectivity to this. In this particular case, if we take propyne and add HX to it, I'm going to add the hydrogen to the carbon with the most hydrogens, and add the X, the nucleophile, to the other carbon. So we get Markovnikov addition with no stereoselectivity for this reaction. And I'll talk a little bit about what happens here, because you only get Markovnikov if it's a terminal alkyne. But same additions that we had before. The additional advantage of a triple bond is you can add not only one HX, but you can add two HXs. So if I wanted to, I could take this molecule and add another molecule of HX, and if I did that, it would then allow me to add, I'd get two X's, two halogens, and then I would get a CH3 group over here. And so I think I've done that reaction down here. If we add two equivalents of HX, then we form this geminal dihalide. So in Wednesday's class, when I said, yeah, you can make triple bonds from geminal dihalides, one of the things that there's a problem with, as we we didn't at the time know how to make geminal halides, but now if we do, the problem is to make a triple bond, you need a triple bond, and that's kind of counterproductive. Okay, so we can add HX. What if I want to do this reaction anti-Markovnikov? Well, just simply take my HX and either add hydrogen peroxide or add an organic peroxide. And now I'm going to add the H and the X anti-Markovnikov. Again, there's no stereoselectivity here. So I would add the HX both trans, and I would add it cis. So another possible product, well, actually the other possible product of this reaction would have the H and the X now cis to each other, and so I would get 50% of this product, 50% of this product, because I would get, because this goes through a radical intermediate. Okay, so anti-Markovnikov, we know how to do that addition. Again, I can add one equivalent of HX, or I could add two equivalents. I could add one equivalent anti-Markovnikov, one equivalent Markovnikov. Okay. So this shows the addition of the two HX molecules. If I want to do bromination with my Br2, if I'm going to add Br2, I'm still going to add the two Brs trans to each other. And so the one equivalent of Br2 will add two Brs trans. If I added a second equivalent of bromine to this, I would then actually form a tetrasubstituted alkane, or a tetrahalide substituted alkane, which I'll show you in the next slide, a couple of examples here. So if we know alkene reactions, we can pretty much know alkyne reactions. And if I can add one equivalent of the reagent to a double bond, I can now add two to the triple bond because it's got two pi bonds. So for the bromine, for instance, if I take my propyne here, and I was to add one equivalent of bromine to this, I would then have added the bromine trans. And then if I added a second equivalent of bromine to this, I would then actually get two bromines attached to each of those carbons that were in the triple bond. And so I would get what's called a 1,2 tetra bromo alkane. So really it's just nothing more than, again, doing two additions of bromine trans, but in this case there's no stereoselectivity overall because there's actually no chiral centers in here. And there's no regioselectivity because I'm adding two bromines. Now, there is regioselectivity when you add HX. And so, for instance, on the previous slide, if I add HCl to propyne, I'm going to end up adding the chlorine to the most substituted carbon, the hydrogen to the least substituted carbon. So if I take a terminal and I react a terminal alkyne, then I'm going to end up forming this alkene. Now, what happens if you have an internal alkyne? Let's just say, for the sake of argument, that I have a methyl group attached to one end of the triple bond and an ethyl. So when I add HCl to this, well, this is carbon A and carbon B, I'm going to end up with two different products because Markovnikov's rule says add the hydrogen to the carbon with the most hydrogens. Well, each of these two carbons has 0 hydrogens. So I'm going to go ahead and add the hydrogen to the right carbon, and then I would have the chlorine added to the left carbon. I'm sorry, add the H to the left carbon, the Cl to the right carbon, and then if I reverse that, I'd have the chlorine added to the left carbon and the hydrogen added to the right carbon. Now, in terms of the stereoselectivity of this, I would not only just get this product, but I would also get the one where the hydrogen and the chlorine added cis. So I would get basically these two products. And then over here, I would also have added the H and the Cl cis. So I would then get these two products as well. So with alkynes, we don't have a lot of freedom. We either have terminal alkynes or internal alkynes. Terminal alkynes are easy because they're Markovnikov. The internal alkynes, if these two groups attached to a triple bond are asymmetric, then I'm going to get a mixture of a whole bunch of products, both from the stereoselectivity aspect, because it's 50-50 cis and trans, but it's also 50-50 then from the regioselectivity point of view. Okay, so that's the only thing we have to really be concerned about with the alkynes is if we have unsymmetrical internal alkynes, then we're going to get actually mixtures of these different products. And so I would have gotten 50% of the two products on the left, 50% of the two products on the right, which means overall would have gotten 25% of each of these products. There's no selectivity involved because of that. Okay. So HX, H, and BR, HX and HX with peroxide, the anti-Markovnikov addition, and the BR2 additions are just very minor extensions of those reactions with double bonds. And the other reaction that is essentially the same as it is for double bonds is oxidative cleavage. Now, what you have to realize when we do oxidative cleavage on a triple bond is because I've got a triple bond with 1 sigma and 2 pi bonds, it's going to require fairly harsh conditions to cleave that triple bond. And so when I was doing cleavage of double bonds, I had some milder conditions like the ozone and the zinc and HCl. Well, those led to the aldehydes being kept intact. In this case, I'm going to require the harshest conditions to split that triple bond. And when I split that triple bond, when I cleave it, I'm going to automatically end up with 2 carboxylic acids because it just requires a wickedly strong reagent to cleave the double bond, and that reagent is also going to then completely oxidize those 2 carbons to carboxylic acids. Again, if you do this reaction, this cleavage reaction with a terminal alkyne, when you split this apart, this part of the molecule is going to become, well, this part of the molecule will become a carboxylic acid. The right side of the molecule will become carbonic acid, and the carbonic acid will basically break apart, will dissociate into CO2 and water. Now, what reagents do I use? I use KMnO4, acid, base, but the key thing is I need heat. So these are pretty harsh. These are pretty harsh conditions in order to make this oxidation occur. I can use ozone and H2O2, but I can't, these have to, all the conditions have to be very harsh for this reaction. And the KMnO4 and base and heat, the key reaction here is going to be it's KMnO4 base and heat. And so with the addition of heat, you'll get the cleavage. Okay, and I say that because there's another reaction that involves the KMnO4 and base, but if that occurs at room temperature, we get a completely different set of products. So it's got to be the harshest oxidizers, KMnO4, acid or base, but key is heat, or ozone and H2O. So you completely cleave the triple bond and make carboxylic acids. What happens with CaMnO4 in basic conditions, and this is a reaction with no heat. Well, what we do is we end up adding OHs to the carbon-carbon triple bond. And so we do cis hydroxylation the same way that we did cis hydroxylation on alkenes. The problem is, since there's two double bonds, we end up putting 4 OHs around this carbon. And once you put the 4 OHs around this carbon, this molecule is not stable. And so what it ends up doing is this molecule ends up losing 2 moles or 2 molecules of water. So this ends up losing 2 H2Os, and it ends up forming what's called a diketone, where the 2 carbonyls are next to each other. So this is a new reaction that's different than what we had for alkenes. The first step isn't. We just added 2 sets of OHs to the triple bond, but then the decomposition to form the diketone is a new step. So you have to remember that this goes all the way to that. Okay. Now, there's some other reactions that are new, and then there's some new twists on them. So if we take a triple bond and we want to reduce it by adding hydrogen, we want to do hydrogenation. If we just use palladium and platinum for this reaction with hydrogen, the first thing that you need to understand is that when we do hydrogenation, we always use an excess of the hydrogen gas because it's very difficult to control just one equivalent of hydrogen. So what happens then is that we know, well, what can we expect for the triple bond? When we add hydrogen to the triple bond, what do you think is going to happen? Well, I'm going to reduce the triple bond down to a carbon-carbon double bond. And how do you think the hydrogens will add? If you said cis, you're right, because that's how hydrogen adds to a triple bond. It's the same mechanism with the hydrogen molecules, sitting on the palladium surface, and then the carbon-carbon triple bond has to come in and approach these hydrogens, and so they'll be added to form the cis alkene. Well, in the presence of excess hydrogen, we now know that the alkene is going to end up being reduced down to the alkane. And so even if I was able to add 1 mole equivalent of hydrogen to this triple bond, some of the triple bond would be reduced, some of the double bond would be reduced, so I'd end up with a whole messy mixture of these products. So what we do is we just simply use excess hydrogen and we do a complete reduction all the way from the triple bond down to the single bond. Okay, so that's complete reduction of the triple bond with hydrogen gas. You might say, yeah, but what if I wanted to stop at the double bond? And then you might say, okay, if I stop at the double bond, wouldn't it be nice if I could make the cis and I could make the trans alkene? Well, you're going to get both of those. So first thing is, how do we add the hydrogens? How do we hydrogenate a triple bond and add them cis? Well, in adding them cis, we add hydrogen and we use what's called the Lindlar catalyst. Now, Lindlar, who's given credit for this catalyst, thought, okay, if the catalyst is so reactive that it'll reduce the triple bond and the double bond, is there any way for me to find a catalyst that will reduce a triple bond but it won't reduce a double bond? And so what he was able to do was to come up with what's called the poisoned catalyst by taking palladium and adding barium sulfate and quinoline and methanol to it. And that poisons the catalyst so that this catalyst can only reduce the triple bond to the double bond. So this catalyst will reduce a carbon-carbon triple bond down to a carbon-carbon double bond, but it's too weak, so it won't reduce a CC double bond to a CC single bond. So using the Poisson-Lindlar catalyst, you just basically add the 2 hydrogens cis to the triple bond, making now the cis alkene. What do you have to know about the Lindlar catalyst? You just have to know the name. I'm not going to ask you for the reagents, and I'm not going to show you these reagents. So the Lindlar catalyst then will reduce triple bonds down to cis alkenes, and it'll stop there. So we can reduce a triple bond all the way down to the single bond, or we can stop it at the cis alkene using H2 in the Lindlar catalyst. And again, here's just kind of that mechanism. You have the hydrogen gas that is adsorbed onto the surface of the palladium. In the Lindlar catalyst case, it's partially poisoned, so that the stereochemistry of this is to add the H's cis to the alkyne. Now, it'd be nice to be able to form a trans alkene, but to do that requires a non-hydrogen method. And so this reagent of taking sodium metal and dissolving it into liquid nitrogen or liquid ammonia is the way that we reduce a triple bond down to a trans alkene. And this is actually a very old method of doing reductions. The sodium metal is the same sodium metal that, it's metallic sodium. Liquid ammonia, you might think, well, wait, ammonia is a gas. You can actually form liquid ammonia. Ammonia liquefies at about, let's say, minus 35 or so degrees Celsius. So you can actually, if you take a round bottom flask and fill it with ammonia gas, and then you put it in something like dry ice, which is solid carbon dioxide, you can actually then get the ammonia gas to liquefy. There's whole apparatuses that'll reflux the liquid ammonia, and it's been 20 years since I've done that reaction, but you can liquefy the ammonia. And what happens is this, and you won't be responsible for this mechanism, but I'm going to show it to you as sort of a why does this reaction add the 2 hydrogens trans? Well, what happens is what starts this process is the following. When you put sodium with its 1 valence electron into liquid ammonia, what happens is that the unpaired electron actually leaves the sodium metal and just becomes like a naked electron that runs around the solution. It's sometimes what's called a solvated electron. The solution, and there's a picture of this in your book, the sodium and liquid ammonia solution turns a deep, dark blue color. And that's what the solvated electron transmits. That's the visible light that it transmits, and it gives the solution a dark blue color. Well, this is the best reducing reagent that you can have. If gaining electrons is reduction, then having just a single electron that you can throw at a molecule is a great way to reduce it. And so what happens in this reaction is the following. That solvated electron adds to the carbon of the triple bond, and when it does so, one of the carbon-carbon pi bonds then moves over here to this carbon. So this is a half arrow, and the other one is a full arrow. So when it's all said and done, this carbon has an unpaired electron on it, and this carbon, the other carbon, has a lone pair. Well, the lone pair, if we added up the charges, the formal charges, this carbon on the right would have a 0 formal charge, and the carbon on the left would have a -1 formal charge. So this is a carbanion. It's a carbon anion, and this is a radical. And so this forms what's called a radical anion species, where we have both a negative charge and an unpaired electron. Now here's the key step in the mechanism. Because these are big clouds of electron density, they orient themselves so that they are trans to each other, because otherwise having two big clouds of electron density cis would repel each other, and that would not be the most stable situation. So having these two big clouds of electron density trans is the more stable situation. Well, then what happens is the C- species deprotonates the nitrogen. We know that from the periodic table, C- is a stronger base than N-. And so this carbanion deprotonates the ammonia, and we end up adding one of the hydrogens onto the double bond. Now I've got just a radical. It's called a vinyl radical again because the unpaired electron is on the carbon with the double bond. So then a second unpaired or second naked electron adds to that radical, now forms an anion, and then that anion then deprotonates the NH to give you the transalkene, with both hydrogens then adding trans across the double bond. But the key species is this radical anion, because these big clouds of electron density have to be trans in order to form a stable situation. And when they do that, that then sets the positions that the hydrogens will add into. Okay, so that's the mechanism. Do you need to know it? No, but if you kind of get stuck and you don't remember if sodium and liquid ammonia adds trans, then if you kind of think about what happens with the naked electron adding to a triple bond, okay, I get two lobes and they have to be trans to each other. Okay, so just to go back here for a second, want to reduce a triple bond all the way down to the single bond, use hydrogen, palladium, and platinum. You want to reduce a triple bond all the way down to a cis alkene, use the Lindlar catalyst, the poisoned palladium catalyst. That'll stop at cis. Want to go down to the double bond but have it trans, use sodium and liquid ammonia. Okay. Now, when you hydrate an alkyne, something weird happens. When you hydrate an alkyne, you actually use H+ and water. Mercury is used as a catalyst in this case, and whether you include the mercury in the reaction or not isn't important. But I'm going to do hydration the same way I did for an alkene, H+ H2O. But notice that the product I make is a ketone. And here's my H and here's my O that added. And so you might say, well, where did that product come from? And it's a good question. So if we were to write the mechanism of this reaction, here's what I would write. I would take my triple bond and add it to the H+. Markovnikov. That's going to give me what's called a vinyl cation. Again, because the plus charge is on a carbon of the double bond. That's what vinyl means. And so then I would have my water, right? I'd have my water, my neutral nucleophile come in, add to this carbon. Get my oxonium ion. And then lose my H+. To form this species, which is actually half alkene, half alcohol, and so this molecule is called an enol. Now it turns out that enols are very unstable. And so enols undergo a reaction to then give me this product, which is called a ketone. Okay, so the first three steps in this mechanism are exactly the same as they would be for a carbon-carbon double bond, except that the enol that I form is unstable and it undergoes a reaction to give me a ketone. Okay, so first three steps we've seen. Let's deal with the last step. So in terms of enols turn out to be very unstable. There are some cases where they are stable, and maybe we'll deal with those next semester. And what they do is they undergo what's called tautomerization. Now, tautomerization is a simultaneous movement of an electron pair and a proton, or electron pairs and a proton. Now, tautomerization is not forming different resonance structures. Resonance structures, you would move electron pairs around, but you don't move atoms. You don't break or make bonds. Tautomerization involves breaking and making bonds, and so it's not resonance structures. So here's I'm going to rewrite my enol here from the last slide. And I'm going to write it like this with my lone pairs. Now I've got my double bond with my hydrogen here and my hydrogen here. So here's my enol. Now what happens is that this is in equilibrium with a ketone. So how do we form the ketone? What happens is that we actually take this pair of electrons and we move it here to form a carbon-carbon double bond. Now if I stop, I got a carbon with 5 bonds, and we know that's bad. So at the same time I move my pair of electrons here to form the carbon-oxygen double bond, I'm going to break this carbon-carbon double bond and I'm going to give it to this carbon. But actually I'm not going to give it to this carbon. I'm going to use that pair of electrons to bond this carbon-hydrogen. So let me put this hydrogen in a box. So the final product that I would get would have a CO double bond, and then that hydrogen that was the OH now ends up added to that carbon. So we take the pair of electrons that were in the double bond and we use it to bind or to bond that hydrogen. So this is a simultaneous movement of electrons, but now I've broken and made a new bond. And so this is tautomerization. And for most enols, they're unstable, and the ketone form is the more stable form. So this is an example of what we would call keto-enol tautomerism. Okay, so our final product then is a ketone. So if I was to do a reaction of this terminal alkyne and react it with H plus H2O. You know, if you want to, you could write the initial product, which would be, in this case, the enol, and then realize that that enol then undergoes tautomerism to form my ketone. So I end up moving this pair of electrons here, moving this pair of electrons up here to form the hydrogen. So this would be my final product of the reaction. Now, when you're doing hydration on symmetrical alkynes, it's a piece of cake, because we just simply would say, okay, I'm going to add my H plus H2O, Markovnikov, but both of the carbons involved in a triple bond have 0 hydrogens. Since this is a symmetrical alkyne, it doesn't matter where I put the H and the OH. So I might say, okay, I'll just put the H here, put the OH here, and then that would undergo tautomerization to then give me the final product of having a CH2 group here and then converting the COH into a ketone. And so if you wanted to, you could add the H to the left carbon or the H to the right carbon. I'm still going to get this molecule where the carbonyl is basically on carbon 2. Now, what happens when I react an unsymmetrical alkyne? Well, what happened when I reacted an unsymmetrical alkyne with HBr? Here's an unsymmetrical alkyne. So if I add H plus H2O to this, what's going to happen? Well, if I add the hydrogen to the left carbon and I add the OH to the right carbon, I'm going to get this enol. If I was to add the OH to the left carbon and the H to the right carbon, then that would give me that enol. And so this enol tautomerizes to form this ketone, and this enol then would tautomerize to form this ketone. And so these are different because here the ketone, the carbonyl is on carbon 2, and over here it's in the middle on carbon 3. Okay, so if you ended up reacting an unsymmetrical alkyne with hydration, you would get a mixture of ketones. When you react a terminal alkyne with H plus H2O, the reaction goes Markovnikov, so you have to add the hydrogen to the end carbon, and then the second carbon becomes the carbonyl. Okay, so a little bit different reaction, but the first few steps are the same. It's just the tautomerization that's brand new. Okay, so you just have to remember that's how that reaction goes. Okay, the final thing for the semester. What happens if you had a terminal alkyne and you wanted to do anti-Markovnikov hydration to then form the enol, the OH, at the end of the chain and have that tautomerize to become an aldehyde? What reagent would you add? Well, what reagent did we add when we wanted to do anti-Markovnikov addition of H and OH to a double bond? If you said BH3, H2O2, you're right. So if I want to do anti-Markovnikov hydration, I'll accept BH3, H2O2. I'll modify this a little bit and show you this has issues, but this is an acceptable molecule because what it would do is it would add the H and the OH, anti-Markovnikov, and cis, although with a terminal alkyne it doesn't matter. So then I would get this enol, and then this enol would undergo tautomerism to form the aldehyde. So I can do Markovnikov or anti-Markovnikov hydration to either form ketones with Markovnikov, aldehydes with anti-Markovnikov. Now, there is a small problem with trying to use BH3 and H2O2 in real life. Yes, I'll give you credit, and I'll probably use BH3, H2O2 myself. But if you tried this in the lab, you might get a mixture of ketones and aldehydes, and you wouldn't get a very high yield of aldehydes, or at least not the highest possible yield. So in this case, what people have come up with is the problem with alkynes is that for Markovnikov and anti-Markovnikov addition, particularly of the BH3, remember the BH3 was set up so that the boron ended up on the least sterically hindered carbon. The issue is that for an alkyne, since it's linear, there's really not that much difference in steric hindrance between the left carbon and the right carbon in this alkyne. And so in order to get better anti-Markovnikov yields, people came up with the idea of using a slightly different boron source than BH3, which is small and could add, basically this boron could end up added to either carbon and be perfectly fine. So what they did was they said, well, we can't make a triple bond more sterically hindered or increase the steric hindrance, the difference in that in a triple bond. So what we'll do is let's make the boron more sterically hindered. And so what they came up with is this molecule called SiA2BH. Its name is disecondary isoamyl borane. The borane part is the boron attached to the hydrogen. The rest of the name should make your skin crawl, because this is like a complete, I'd use a B word here, of this of the IUPAC and common naming system. It's just a completely screwed up system that they used. First of all, isoamyl. Amyl is the older term for pentyl. So we have isoamyl, and then we have disecondary, and it's like, is that common name? Is it IUPAC name? It's neither, but this is what people call it. So this is actually a secondary isoamyl, really. Well, this is a 5-carbon chain. It's got the iso group, so therefore it's isoamyl, and the boron's attached to a secondary carbon. None of the IUPAC rules would accept this as an appropriate name, but what it does is it creates a very sterically hindered molecule. And now, with a sterically hindered reagent, the difference between the terminal end and the internal end of the triple bond is now sort of accentuated, so that the boron then is more likely of this. The boron is definitely more likely to end up on the terminal carbon. And so what that means is when you treat it with hydrogen peroxide, you're going to get that enol formed at a higher percent yield. So this is the reagent that you'll see in your textbook, is the disecondary isoamyl, which is SiA2, which is secondary isoamyl square for two of those, and then the BH. But I would give you credit for BH3 and H2O2. Okay. Okay, so this finishes up the reactions of alkynes. So we've been through preparations of alkynes and now reactions of alkynes. There's only a couple of new reactions here. The rest of them are basically, hopefully you still remember from alkenes. And if you don't remember them from alkenes, you better get that back in your head for Monday or Wednesday of next week. Okay, so I will be posting an online quiz. We will have an in-class quiz on Wednesday over the reactions that we talked about Wednesday in class. And if you have any questions about these, we'll probably do some problems with these reagents on Friday just to reinforce that. But if you have any questions about this, bring them to class on Friday, the last day.